solving problems by searching, in which we see an agent can find a sequence of actions that achieves its goals when no single action will do. The simplest agents discussed in Chapter 2 were the reflex agents, which base their actions on a direct mapping from states to actions. Such agents cannot operate well in environments for which this mapping would be too large to store and would take too long to learn. Goal-based agents, on the other hand, can succeed by considering future actions and the desirability of their outcomes. This chapter describes one kind of goal-based agent called a problem-solving agent. Problem-solving agents decide what to do by finding sequences of actions that lead to desirable states. We start by defining precisely the elements that constitute a problem and its solution, and give several examples to illustrate this definition. We then describe several general-purpose search algorithms that can be used to solve these problems and compare the advantages of each algorithm. The algorithms are informed, in the sense that there are no information about the problem other than its definition. This chapter uses concepts from the analysis of algorithms. Intelligent agents are supposed to maximize their performance measure. As we mentioned in Chapter 2, achieving this is sometimes simplified if the agent can adopt a goal and aim at satisfying it. Let us first look at why and how an agent might do this. Imagine an agent in the city of Arad, Romania, enjoying a touring holiday. The agent's performance measure contains many factors. It wants to improve its Santon, improves its Romanian, takes in the insight, enjoy the nightlife, avoid hangovers, and so on. The decision problem is a complex one involving many trade-offs and careful reading of guidebooks. Now, suppose the agent has a non-refundable ticket to fly out of Bucharest the following day. In that case, it makes sense for the agent to adopt the goal of getting to Bucharest. Courses of action that don't reach Bucharest on time can be rejected without consideration, and the agent's decision problem is great. Goals help organize behavior by limiting the objectives that the agent is trying to achieve. Goal formulation, based on the current situation and the agent's performance measure, is the first step in problem solving. We will consider a goal to be a set of world states exactly to those states in which the goal is satisfied. The agent's task is to find out which sequence of actions will get it to a goal state. Before it can do this, it needs to decide what sorts of action and states to consider. If it were to try to consider actions at the level of move the left foot forward an inch or turn the steering wheel 1 degree left, the agent would probably never find its way out the parking lot, let alone to Bucharest, because at the level of detail there is too much uncertainty in the world and there would be too many steps in a problem formulation is the process of deciding what actions and states to consider, given a goal. We will discuss this process in more detail later. For now, let us assume that the agent will consider actions at the level of driving from one major town to another. The states it will consider therefore correspond to a being in a particular town. Our agent has now adopted the goal of driving to Bucharest and is considering where to go from Arad. There are 3 roads out of Arad, one towards Sibiu, one to Timisoara, and one to Zărin. None of these achieves the goal, so unless the agent is very familiar with the geography of Romania, it will not know which road to follow. In other words, the agent will not know which its possible actions is best, because it does not know enough about the state the results from taking its action. If the agent has no additional knowledge, then it is stuck. The best it can do is choose one of the actions at random. This process of looking for such a sequence is called search. A search algorithm takes a problem as input and returns a solution in the form of an action sequence. Once a solution is found, the action it recommends can be carried out. This is called the execution phase. Thus, we have a simple formulate search execute design for the agent. After formulating a goal and a problem to solve, the agent calls a search procedure to solve it. It then uses the solution to guide its actions, doing whatever the solution recommends as the next thing to do. Typically, the first action of the sequence and then removing the step from the sequence. Once the solution has been executed, the agent will formulate a new goal. A simple problem-solving agent. It first formulates a goal and a problem, searches for a sequence of actions that would solve the problem, and then executes the actions one at a time. When this is complete, it formulates another goal and starts over. Note that when it is executing the sequence, it ignores its first steps. It assumes that the solution it has found will always work. Well-defined problems and solutions. A problem can be defined formally by four components: the initial state, the successor function, the goal test, and the path cost. The initial state that the agent starts in. A description of the possible actions available to the agent. The most common formulation uses a successor function. The goal test, which determines whether a given state is a goal state. Sometimes there is an explicit set of possible goal states, and the test simply checks whether the given state is one of them. A path cost function that assigns a numeric cost to each path. The problem-solving agent chooses a function that reflects its own performance measure. This is a simplified roadmap of part of Romania. The initial state here for our agent in Romania may be described as initial arad. The successor function given a particular state x successor minus fn of x returns a set of action and successors. Ordered pairs where each action is one of the illegal actions in state x and each successor is a state that can be reached from x by applying the action. The goal test in Romania is the singleton set in Bucharest. Sometimes the goal is specified by an abstract property rather than an explicit enumerated set of states. For example, in chess, the goal is to reach a state called checkmate, where the opponent's king is under attack and cannot escape. A path cost. For the agent trying to get to Bucharest, time is the essence, so the cost of a path may be its length in kilometers. In this chapter, we assume that the cost of a path can be described as the sum of the costs of the individual actions along the path. Formulating problems. In the preceding section, we propose a formulation of the problem of getting to Bucharest in terms of the initial state, successor function, goal test, and path cost. This formulation seems reasonable, yet it omits a great many aspects of the real world. Compare the simple state description we have chosen in Arad to an actual cross-country trip where the state of the world includes so many things. Example problems. The problem-solving approach has been applied to a vast array of task environments. We list some of the best known here, distinguishing between a toy and a real-world problems. A toy problem is intended to illustrate or exercise various problem-solving methods. It can be a concise, exact description. This means that it can be used easily by different researchers to compare the performance of algorithms. A real-world problem is one whose solution people actually care about. They tend not to have a single agreed-upon description, but we will attempt to give the general flavor of their formulation. Toy problems. The first example we will examine is the vacuum world, first introduced in Chapter 2. This can be formulated as a problem as follows. States, the agent is in one of two locations, each of which might or might not contain dirt. Thus, there are 2 times 2 to second power equals to 8 possible world states. Initial state. Any state can be designated as the initial state. Successor function. This generates the legal states that result from trying the 3 actions, left, right, and sock. Goal test. This checks whether all the squares are clean. Path cost. Each step costs 1. So the path cost is the number of steps in the path. The 8 puzzle. It consists of a 3 by 3 board with 8 numbered tiles and a blank space. A tile adjacent to the blank space can slide into the space. The object is to reach a specified goal state. The goal of the 8 queens problem is to place 8 queens on a chessboard such that no queen attacks any other. A queen attacks any piece in the same row, column, or diagonal. Here shows the attempted solution that fails. The queen in the rightmost column is attacked by the queen at the top left. Although efficient special-purpose algorithms exist for this problem and the whole n queens family, it remains an interesting test problem for search algorithms. There are 2 main kinds of formulation: an incremental formulation, which involves operator that augments the state description, starting with an empty state. For the 8 queens problem, this means that each action adds a queen to the state. A complete state formulation starts with all 8 queens on the board and moves them around. In either case, the path cost is of no interest because only the final state counts. The first incremental formulation one might try is the following. States. Any arrangement of 0 to 8 queens on the board is a state. Initial state. No queens on the board. Successor function. Add a queen to any empty square. Goal test. 8 queens are on the board. None attack. Real-world problems. We have already seen how the route-finding problem is defined in terms of specified locations and transitions along links between them. Route-finding algorithms are used in a variety of applications, such as routing in computer networks, military operations planning, and airline travel planning systems. These problems are typically complex to specify. States. Each is represented by a location and the current time. Initial state. This is specified by the problem. Successor function. This returns the states resulting from taking any scheduled flight, leaving later than the current time plus the within-airport transit time from the current airport to another. Goal test. Are we at the destination by some pre-specified time? Path cost. This depends on monetary costs, waiting time, flight time, customs and immigration procedures, seat quality, time of day, type of airplane, frequent flyer, meal age awards, and so on. The traveling salesperson problem, or TSP, is a touring problem in which each city must be visited exactly once. The aim is to find the shortest tour. The problem is known to be NP-hard, but an enormous amount of effort has been expended to improve the capabilities of TSP algorithms. In addition to planning trips for traveling salespersons, these algorithms have been used for tasks such as planning movements of automatic circuit board drills and of stocking machines on shop floors. A VLSI layout problem requires positioning millions of components and connections on a chip to minimize area, minimize circuit delays, minimize stray capacitances, and minimize manufacturing yield. The layout problem comes after the logical design phase and is usually split into two parts: cell layout and channel routing. In cell layout, the primitive components of the circuit are grouped into cells, each of which performs such recognized function. Each cell has a fixed footprint, size and shape and requires a certain number of connections to each of the other cells. The aim is to place the cells on the chip so that they do not overlap and so that there is room for the connecting wires to be placed between the cells. Channel routing finds a specific route for each wire through the gaps between the cells. These search problems are extremely complex but definitely worth solving. Robot navigation is a generalization of the route finding problem described earlier. Rather than a discrete set of routes, a robot can move in a continuous space with an infinite set of possible actions and states. For a circular robot moving on a flat surface, the space is essentially two-dimensional. When the robot has arms and legs or wheels, that must also be controlled. The search space becomes many-dimensional. Advanced techniques are required just to make the search space finite. We examine some of these methods in the next chapters. In addition to the complexity of the problem, real robots must also deal with errors in their sensors reading and motor controls. Automatic assembly sequencing of complex objects by a robot was first demonstrated by Freddie Michi 1972. Progress since then has been slow but sure, to the point where the assembly of intricate objects such as electric motors is economically feasible. In assembly problems, the aim is to find an order in which to assemble the parts of some object. If the wrong order is chosen, there will be no way to add some part later in the sequence without undoing some of the work already done. Checking a step in the sequence for feasibility is difficult. Geometrical search problem closely related to robot navigation. Thus, the generation of legal successor is the expensive part of assembly sequencing. Any practical algorithm must avoid exploring all but a tiny fraction of the state space. Another important assembly problem is protein design, in which the goal is to find a sequence of amino acids that will fold into a three-dimensional protein with the right properties to cure some disease. Searching for solutions. Having formulated some problems, we need to solve them. This is done by a search through the state space. Search techniques that use an explicit search tree that is generated by the initial state and the successor function that together define the state space. In general, we may have a search graph rather than a search tree, when the same state can be reached from multiple paths. The root of the search tree is a search node corresponding to the initial state. The first step is to test whether this is a goal state. Clearly it is not, but it is important to check so that we can solve trick problems. Because this is not a goal state, we need to consider some other states. This is done by expanding the current state, that is, applying the successor function to the current state, thereby generating a new set of states. We also need to represent the collection of nodes that have been generated but not yet expanded. This collection is called the fringe. Each element of the fringe is a leaf node. Measuring problem-solving performance. The output of a problem-solving algorithm is either failure or a solution. We will evaluate an algorithm's performance in 4 ways. Completeness. Is the algorithm guaranteed to find a solution when there is one? Next, optimality. Does the strategy find the optimal solution? Time complexity. How long does it take to find a solution? Space complexity. How much memory is needed to perform the search?
This article covers 5 strategies in which all we know about the problem is its definition and no additional information about the states beyond the story in the problem definition. Informed search strategies are very systematic, and all they can do is expand nodes using the successor function and check whether each state is a full state or not. Search strategies that we will talk about are breadth-first search, uniform cost search, depth-first search, iterative deepening search, and bidirectional search. Breadth-first search, a simple strategy which the root is expanded first and all the root successors are expanded next, then their successors. We visit search tree level by level that all nodes are expanded at a given depth before any nodes at the next level are expanded. Breadth-first search can be implemented by calling tree search with an empty fringe that is a first-in first-out queue, assuring that the nodes that are visited first will be expanded first. The FIFO queue puts all newly generated successors at the end of the queue, which means that shallow nodes are expanded before deeper nodes. Breadth-first search is optimal when all step costs are equal, because it always expands the shallowest unexpanded node. By simple extension, we can find an algorithm that is optimal with any step cost function. Instead of expanding the shallowest node, uniform cost search expands the node n with the lowest path cost. Uniform cost search does not care about the number of steps a path has, but only knows about their total cost. This condition is also sufficient to ensure optimality. It means that the cost of a path always increases as we go along the path. Therefore, the first goal node selected for the expansion is the optimal solution. Remember that tree search applies the goal test only to the nodes that are selected for expansion. We recommend trying the algorithm out to find the shortest path to Bucharest. Depth-first search is a simple strategy or an algorithm for traversing or searching tree or graph data structures. DFS progresses by expanding the first child node of search tree that appears, and thus going deeper and deeper until a goal node is found, or until it hits a node that has no children. Then the search backtracks to turn into the most recent node it hasn't finished exploring. DFS was implemented by calling tree search, last in first out queue. Non-recursive implementation of DFS. Deepening search is a general strategy often used in combination with depth first search that finds the best depth limit. Iterative deepening search is analogous to breadth first search in that it explores a complete layer of new nodes at each iteration before going on to the next layer. Bidirectional search. The idea behind bidirectional search is that two simultaneous searches, one forward from the initial state and the other backward from the goal, stopping when the two searches meeting. Checkmate goal test in chess. A backward search would need to construct compact descriptions of all states that lead to checkmate when move m symbol, and so on. And those descriptions would have to be tested against the states generated by the forward search. There is no general way to do this efficiently.
Avoiding repeated states. We have all but ignored one of the most important complications to the search process. It is the possibility of wasting time by expanding states that have already been encountered. So first, for tree search, this possibility never comes up. In the space tree, there is only one path to each state. Example, 8 queens where new queen are placed at the leftmost column. Repeated states are unavoidable. It is unavoidable such as the root finding problems and sliding block puzzles. The search trees for these problems are finite. So in this picture, the more realistic is the picture C, because each has 4 state successors, so the search tree including repeated states has 4 raised to d leaves, but there are only 2d raised to 2 distinct states. For example, if d is equals to 20, this means about a trillion nodes but only 800 distinct states are available. For depth search, the only nodes in the memory are those on the path from the root to the current node. So comparing those nodes to the current node allows the algorithm to detect the looping paths that can be discarded immediately. This makes sure that the finite states do not become infinite. If the current nodes matches a node in the closed list, it is discarded instead of being expanded. The new algorithm is called graph search. On problems of repeated states, this is much more efficient than the tree search. So in this given problem segment, the general graph search algorithm, the search closed, can be implemented with a hash table to allow efficient checking for repeated states. This algorithm assumes that the first path to a state S is the cheapest. Searching with partial information. Sensorless problems, also called as conformant problems. If agent has no sensor at all, then it could be one of several possible and initial states, and each might lead to one of several possible successor states. Contingency problems. If the environment is partially observable or if actions are uncertain, then the agent's percepts provide new information after each action. So in the given example, we will use the vacuum world environment. Let's recall it has 8 states. There are 3 actions, which is the left, right, and then sock. And the goal is to clean up all the dirt. If the environment is observable, deterministic, and completely known, then the problem is initially solvable by any algorithm we described. For example, if the initial state is 5, then the action requires is right and sock. If we do that, we will reach the goal 8.